Welcome to another engineering instructional snippet. In this video we will be calculating the hydraulic power delivered by a pump. Here is the problem statement. Calculate the power in kilowatts the pump is delivering to the water for the given conditions. Neglect all losses. Neglecting all losses doesn't sound very reasonable, but in fact this approach is very useful. The losses that occur in the pump impact the pump efficiency. I will have additional snippets that demonstrate how to calculate the shaft power to the pump, but the first step will be to calculate the hydraulic power as we will in this video. These are the main equations that we will be using. Conservation of energy, in dimensions of energy per unit weight, which is length. Hydraulic pump power. And volumetric flow rate. Let's solve the energy equation for the pump head. Next we will simplify. We will set the loss term to 0. We will ignore any elevation change across the pump. This is a typical assumption in the analysis of most pumps and turbines. Let's look at the data for this problem. Point 1 is the pump inlet. P1 is 100 kilopascals. D1 is 10 centimeters. Point 2 is the pump outlet. P2 is 500 kilopascals. D2 is 5 centimeters. The volumetric flow rate, Q, is 60 cubic meters per hour. Let's find the velocities at points 1 and 2 using the provided data. Taking care of units, we get the results shown here. Earlier we solved the energy equation for the head of the pump. Let's simplify that result further as shown here. Before we plug in numbers, let's check units. In fact, getting the units correct is often the most challenging part of these types of problems. The pump head should come out in meters. You will see below that we are expanding the Newton into its native units. The results indicate that our units are good, but it wasn't easy. Now we are ready to plug in numbers and calculate the pump head. The results are shown below. It is interesting to note that most of the energy added by the pump goes into an increase of pressure. This is not surprising. In fact, if the diameter of the pump outlet is equal to the pump inlet, then all of the energy goes into the pressure term. This result is good, but we are looking for the hydraulic power. Pump head is energy per weight, so we multiply it by weight flow per unit time to get power. The equation is shown here. Let's plug in numbers and units. Once again, not making errors with units is the greatest challenge. The end result is that this pump is delivering 7.23 kilowatts to the water. Pump hydraulic efficiency is typically between 0.5 and 0.75, so the power delivered to the pump will be significantly greater, but that will be covered in another instructional snippet. I hope you found this instructional snippet useful. If so, then please like and subscribe. Thank you and have a great day.